Ever get that feeling, like the universe is just messing with us? Like we think we've got it all figured out, all these laws of physics, these beautiful theories,
Right.
and then, bam, something pops up. Something totally weird that makes you question everything.
Throws a wrench in the works.
Exactly.
Okay.
And that's what we're diving into today, those cosmic curveballs, those space oddities, as physicist Harry Cliff so aptly calls them.
Ah, yes.
And we've got his book right here, QW Space Oddities. Don't worry, it's not as intimidating as it sounds.
No, not at all.
Cliff's a great storyteller. And trust me, the stories behind these scientific mysteries are anything but dull.
Oh, they're fascinating.
So imagine this physics. It's like this perfectly ordered house of cards, right?
Okay.
Everything's in its place. And then suddenly you see one card just floating in midair.
Defying gravity.
Exactly. That's kind of what an anomaly feels like to a scientist. Sometimes figuring out why that card is floating, that leads to like a whole new wing being added to the house of cards. But sometimes it's just, well, a really weird breeze.
Exactly. And those weird breezes, those anomalies that don't lead to immediate breakthroughs, they're still so important. They keep us on our toes, always testing, always refining our understanding.
So it's not just about finding the right answers, it's about asking the right questions.
Precisely.
I like that. So give us an example. What's like a classic anomaly that really forced physicists back to the drawing board?
Well, let's take a trip back in time, shall we? Back to the 19th century. Astronomers, with their meticulous observations, they had the solar system pretty much figured out, all thanks to Newton's law of gravity, of course.
Newton, the OG.
Indeed. But then, there was Mercury.
Ah, Mercury. Always the troublemaker, even on a cosmic scale, right?
Right.
What was going on with Mercury?
Well, Mercury's orbit, that elliptical path around the sun, it had this tiny wobble, a slight deviation from what Newton's laws predicted.
No.
It wasn't much, but it was enough to drive astronomers absolutely bonkers. They even came up with this hypothesis, you see, of a hidden planet lurking too close to the sun for us to see directly.
A hidden planet.
They called it Vulcan. They figured Vulcan's gravity must be messing with Mercury's orbit.
Wow. So they invented a whole planet just to try and make the math work. Talk about dedication. Did they ever find this elusive Vulcan?
Well, after years of searching, it became pretty clear that Vulcan was about as real as, say, a unicorn riding a dragon.
Okay, that's a visual.
The answer to Mercury's wonky orbit turned out to be far more profound, and it came from a rather revolutionary fellow named Albert Einstein.
Einstein. Always a good bet when things get cosmically confusing. So how did Einstein explain this whole Mercury situation?
Well, Einstein's theory of general relativity completely changed our understanding of gravity. He said it wasn't simply a force acting at a distance, but rather that massive objects, like the sun, actually warp the fabric of space-time itself.
Okay, warp the fabric of space-time.
Imagine a bowling ball placed on a trampoline. It creates a dip, right?
Yeah, I can picture that.
So think of the sun as that bowling ball. And the planets, well, they're moving through this warped space-time.
Okay, I'm with you.
Yeah.
So the sun is the bowling ball, the planets are, well, not exactly marbles, but,
Precisely. And because Mercury is so close to the sun, it's much more sensitive to this warping effect, this curvature of space-time, that slight discrepancy that had those 19th century astronomers in a tizzy.
Yeah.
It was actually the first piece of evidence that Einstein's theory of general relativity was on the right track.
Wow. That's incredible. So a tiny wobble in Mercury's orbit basically confirmed one of the most groundbreaking theories in physics. From wonky orbits to warped space-time, amazing. What about the quantum realm? Any good mysteries hiding out there?
Oh, the quantum world is practically bursting with them. But there's one particular head-scratcher that really stands out. It all started in 1947 with a physicist named Willis Lamb. He was making incredibly precise measurements of the energy levels within a hydrogen atom.
Okay, hydrogen atom, energy levels.
Think of it this way. The energy levels within an atom, they're like rungs on a ladder. An electron, it can only exist on those rungs, not in between.
Okay, got it. So what did Lamb find on those energy rungs?
Well, the prevailing theory at the time, and it was a pretty solid theory, mind you, said that two of these energy rungs, we'll call them S and P, should be at the exact same height.
Right.
But when Lamb took his measurements, he found a tiny difference between them. A discrepancy of only 1 part in a million.
1 part in a million. That sounds almost negligible. Why was everyone so worked up about it?
Because in the quantum world, even the tiniest discrepancies can shatter the foundation of a theory. It's like, imagine you're walking up a staircase and one of the steps is, I don't know, a millimeter higher than the others. You might not even notice it normally, but it could trip you up if you're not careful.
I see, yeah. So it's about the principle of the thing. So this tiny discrepancy, this 1 part in a million thing.
The Lamb shift. Yeah.
The Lamb shift, right. It caused a major freak out in the physics world.
Oh, absolutely. It meant that our understanding of how light and matter interact, like at the most fundamental level, it was missing something big.
So not just a crack in the foundation, more like the foundation was built on, I don't know, a giant marshmallow or something.
Well, you get the idea. It was a big deal. And this discovery, it led to the development of quantum electrodynamics, QED for short.
QED? Catchy.
And QED, it didn't just explain the Lamb shift, it became the most precisely tested theory in physics. Laid the groundwork for understanding things like lasers, superconductors.
Okay, now we're talking. From a tiny atomic blip to lasers and superconductors, that's pretty impressive. So we've seen how these anomalies can really shake things up, in a good way. But what about the mysteries that are still unsolved? The ones that still have physicists, like scratching their heads, burning the midnight oil. Any space oddities out there right now that are particularly baffling?
Oh, absolutely. And one that really captures the imagination. It involves neutrinos, those ghost particles that can pass through, well, practically anything.
Neutrinos, right. Ghost particles. So what's the mystery with them? What's keeping physicists up at night?
Well, it starts with our own star, the sun. Deep down in its core, the sun's like a giant fusion reactor.
Right, churning out energy.
Exactly. And as a byproduct, it's producing a whole lot of neutrinos.
Okay.
So scientists, they set out to measure these solar neutrinos.
Makes sense.
But here's the thing. They were finding far fewer than expected. It's like, imagine a third of the sun's neutrinos just vanished into thin air.
Wait, so is the sun like running out of neutrinos? Is that a thing we should be worried about?
No need to panic. The sun's doing just fine. It's our understanding of neutrinos that needed an upgrade. Turns out neutrinos are even sneakier than we thought. They can actually change their flavor as they travel through space.
Change their flavor? Okay, now you're just messing with me.
No, really. They oscillate between 3 types. Electron neutrinos, muon neutrinos, and tau neutrinos.
So it's like they're changing costumes or something, making them even harder to track. Okay, so that's kind of cool, I guess, but does this flavor changing explain the missing neutrinos from the sun?
It's a big part of the puzzle, for sure. By accounting for neutrino oscillations, we've gotten closer to matching what we observe with what we'd expect. But some experiments, they hint that there might be even more to the story.
More. Okay, I'm intrigued. Tell me more.
There's a chance, and this is where things get really interesting, that a 4th type of neutrino exists. A sterile neutrino.
A sterile neutrino. All right, that sounds serious. What's so special about this sterile neutrino? What makes it stand out from its more flavorful cousins?
Well, unlike the other neutrinos, this one wouldn't interact with matter through the weak force, one of the 4 fundamental forces in the universe.
Right, the 4 fundamental forces.
It would be even more elusive, only interacting through gravity.
So we're talking about a particle that's practically invisible, even more than the other neutrinos. Why would scientists even think something like that exists?
Because sometimes the best explanation for what we can see is what we can't see. It's like, imagine you're trying to balance a seesaw. One side seems lighter than it should be, right? Maybe there's something invisible on the other side, counteracting the weight.
Okay, I get the analogy. So how does this invisible neutrino, this sterile neutrino, how does that tie into all of this?
Well, some physicists believe that sterile neutrinos, if they exist, could help explain one of the biggest mysteries in cosmology: dark matter.
Dark matter, the stuff that makes up a huge chunk of the universe, but we can't seem to detect directly.
Exactly. And while sterile neutrinos haven't been directly detected yet, if they exist and they have the right properties, they could potentially make up a significant portion of that dark matter.
Wow. So from wonky orbits to warped space-time and now to ghostly neutrinos, potentially explaining the unseen universe. The universe has a way of keeping us on our toes, doesn't it? It's like we're just scratching the surface of all these cosmic mysteries. What about like those really big mysteries, the ones on like a universal scale?
Ah, now you're talking cosmology, where things get really interesting.
Right, cosmology. Okay, so hit me with it. What are some of the big cosmological space oddities that have everyone stumped?
Well, there's one called the Anita anomaly.
Anita anomaly. Okay, that sounds a little ominous. What is that?
So Anita stands for Antarctic Impulsive Transient Antenna.
Okay.
And it's this really incredible instrument, basically a detector suspended from a giant balloon.
A giant balloon.
Floating high above Antarctica.
Antarctica. Wow. So we're talking extreme science, huh? Dealing with cosmic mysteries and like blizzards and stuff.
Yeah.
So what's Anita doing down there? Or up there, I guess.
It's designed to detect radio waves, but not just any radio waves. It's listening for these specific radio waves that are produced when ultra-high energy neutrinos interact with the Antarctic ice.
Ultra-high energy neutrinos, so like super-powered ghost particles.
Exactly. And these neutrinos, they have energy levels way beyond anything we can create in a lab.
Okay, so big, powerful stuff. Why go all the way to Antarctica to find them?
Well, that's where things get weird. Anita, it detected something that, according to everything we know about physics, shouldn't be possible.
Okay, I'm officially intrigued. Tell me more.
It detected what looked like upward-going cosmic rays.
Upward go, you mean like coming from the Earth?
Yeah.
But don't neutrinos like pass through the Earth all the time?
Right, most neutrinos do. They barely interact with matter at all, but these were different. These upward-going cosmic rays, that's what they were. They had such high energy that they should have hit something on their way through the Earth. They should have been stopped.
Oh, wow. Okay, that is weird. It's like, I don't know, watching a bowling ball go right through a wall. How is that even possible?
That's the million-dollar question. Scientists are looking at a bunch of different possibilities. Some think it might be something about the Antarctic ice itself.
Okay.
Maybe it's reflecting the cosmic rays in some unexpected way. Others think it could point to new physics beyond what we currently understand.
New physics. So, like, the standard model of particle physics, the one we've all come to know and love, it's not like the whole story.
It's possible. And, one of the candidates for explaining these upward-going cosmic rays.
Let me guess. Sterile neutrinos.
Bingo. If they exist, and if they interact with other particles in ways we haven't figured out yet, well, they could potentially explain what Anita's seeing.
Sterile neutrinos. Always at the center of the action. But there's another big mystery you mentioned, something about the expansion of the universe.
Ah, yes. The Hubble tension. Have you heard about this one?
I've heard the term, but to be honest, I don't really know what it's all about. Is it like surface tension, but on a cosmic scale?
Not quite, but it does have to do with something pretty fundamental, how fast the universe is expanding. We measure that expansion using something called the Hubble constant.
A Hubble constant, right?
And the thing is, there are a couple of different ways to measure the Hubble constant. We can look at the afterglow of the Big Bang, the cosmic microwave background radiation, or we can measure the distances and speeds of galaxies that are relatively close to us.
Okay, so two different ways to measure the same thing. Sounds pretty straightforward. What's the problem?
The problem is, those two methods, they give us slightly different answers for the Hubble constant.
Oh, so that's the tension.
Exactly. And the difference is big enough that it's got everyone scratching their heads. It can't be explained away by just simple measurement errors.
So what does it mean? The universe isn't expanding at the rate we thought it was?
It might be that our current understanding of cosmology is missing something. Some physicists think this Hubble tension could be evidence of new kinds of particles or fields that influenced the early universe. Things we haven't even discovered yet.
Wow. So much we don't know. It's kind of mind-blowing, actually.
It really is. And that's what makes these space oddities so fascinating. They're not just these abstract puzzles. They're windows into the unknown. They remind us that our understanding of the universe is constantly evolving.
Yeah, it's like the universe is this giant puzzle, and we're just starting to put the pieces together.
Exactly. And every anomaly, every discrepancy, it forces us to question our assumptions, refine our theories, and come up with new ways to explore the cosmos.
And who knows what amazing breakthroughs might come from all of this. I mean, maybe sterile neutrinos will be the key to understanding dark matter, or maybe this Anita anomaly will lead us to a whole new realm of physics, or maybe, just maybe, there are even stranger things out there just waiting to be discovered.
You said it. The universe is full of surprises, and that's what makes science, that's what makes this whole journey of discovery so exciting.
Absolutely. It's a good reminder that we should never stop asking questions, never stop exploring. Well, that's about all the time we have for today, but wow, what a deep dive this has been. Thanks so much for joining us, and as always, keep looking.